Hello, my name is Garrett Andreessen. I will be taking a look into the compression and deployment of a neural network-based chess engine. So the main issue that I'm trying to solve is to create a chess engine that uses neural networks to make the decisions for it, and this model is then compressed using three types of compression: weight clustering, weight pruning, and quantization. And after all the compression, the model will be able to run significantly better on a Raspberry Pi. So there's a lot of motivation into looking into this issue. Chess is not a solved game. There are too many factors, and this is why we use neural networks to look at them. And in addition, compression is a really important issue because it can make the model smaller, which can allow it to fit into memory and significantly speed up the inference time. This challenge is very technically challenging because we want to look as far into the future as possible. So this is a table showing the amount of board states looking from the starting position at different depths. So we want to look as deep as possible to find the best move. It's also challenging because we need to find a good trade-off between size and loss when doing compression, and the deployment was a challenge because integrating two different code sources was very tough. There are a few related works pertaining to my problem. So Deep Chess is the most famous neural network-based chess engine and is the first of its kind to be able to beat grandmasters. Deep Chess does not know the rules of chess. Instead, it uses unsupervised learning to extract features and supervised learning to compare two board states. Another related work is Deep Compression, which we read about for one of our reading assignments. This paper talks about how it uses pruning and quantization, followed by Huffman encoding, to compress models significantly, up to 35 to 49 times their original size. To begin this project, I began generating data. So a random board state was generated, and then this board state was one hot encoded. Each unique color and piece gets its own 8x8 matrix. So on top of this, two more were added to show what squares white and black can reach. So in this example, you see these three pawns here. Those can be seen right here in this left matrix, and same thing with these three pawns. And then this matrix on the right shows the squares that black can reach. So we see this bishop can go all the way down here, so we see those ones right there. And so the final input shape is 14 by 8 by 8, and the output is a normalized evaluation of the board between 0 and 1. So this is my original model. It's very simple, made up of 2D convolution layers and a few dense layers. The simplicity helps because it gets called so many times. I tried using a residual network, but it did not work as well as this simple network. After this, compression was done. So the first type of compression was weight clustering, which reduces the number of unique weights in the network. After that, there was weight pruning, which gets rid of unnecessary weights and neurons. And then there was quantization, which converts the 32-bit floating points into integers in this cage, which take up less space, and the hardware is better optimized for them. So the last thing that was done was the model was deployed on a Raspberry Pi 3. This was integrated with my code from my last project, and this deployment let me check more things than if it was not deployed. So in this example over here, the engine is playing as white, I am playing as black. So the engine will light up a single square, and that's the piece that it would like to move, and then it lights up the square it would like to move that piece to. And then when black goes, they select a piece, and all of the legal moves light up for that piece, and they must choose one of them. The compression of the model was a huge success. The original size of the model was 3.03 megabytes, and the final size was 0.07, about 43 times as small as the original model. So the original model had an MAE of 0.0097, and the final model had an MAE of 0.019, which means there was an increase of about 0.0093 MAE, and it should be noted that MAE is being used here instead of MSE because the results are normalized between 0 and 1. And so what this 0.019 means is when the model gives an evaluation, it is off by an average of 1.9%. And so the model size can be visualized throughout the compression process compared to the mean absolute error. In addition to that, each of the uncompressed models and compressed models played Stockfish 13, 25 times, and these are some of the metrics after that. So as you can see, the uncompressed model does slightly better, but nothing too significant. And then one last thing that I tested was the speed up, and this was tested by generating 2,000 boards and one hot encoding them, and then they ran through the original model and then the compressed model. So it took the uncompressed model 47.3 seconds, and it took the compressed model 4.5 seconds. This is about a 10 times speed up, and this is very significant and can definitely help me increase the depth of my model. I feel like this model could make a big impact. As each year, neural networks keep on getting larger, and compression will be needed to keep up, especially if deployed on an IoT embedded or mobile device. And this was the first chess engine I could find with a focus on compression. And this could lead the way for other chess engines or models. A 10 times speed up is great and could have significant impacts on other models. There's a lot of future works that I believe this project could go into. The best way to improve the chess aspect would be to add search optimizations, such as alpha beta pruning, which is extensively used in modern chess engines, and the other would be to optimize the model a little bit more. I think the normalized values could be giving some issues, so I would change this to a non-normalized value. And I would also use some better training data, like some grandmaster games. And these are my references. Thank you for listening to my presentation.